So we're next going to talk about conductors in electrostatic equilibrium. And what's meant by static equilibrium is that any charges on the conductor have been given a chance to find their equilibrium position. And we begin with the idea in the red box. One important property of conductors in static equilibrium is that the charges will rearrange until the electric field inside the conductor is zero. And a proof of that can be seen by thinking about the points that follow. The first is that if any excess charge is placed on a conductor, it is going to move until the charges find a position where they are at static equilibrium. And what's meant by that is that the net force acting on that excess charge is equal to zero. And if it isn't equal to zero, then the charges continue to move. And so when it reaches equilibrium, it means that the charges are no longer experiencing a net force that will drive them, and so they'll have reached their equilibrium position. And if the charges are no longer feeling a force when they reach that equilibrium position, it means that the electric field is going to be equal to zero everywhere inside the conductor. Otherwise, they would feel a force, F equals QE. So if the force on the charges has gone to zero, that means the electric field has gone to zero within the conductor. So we will be able to assume when we're solving problems that involve conductors in static equilibrium that the electric field inside the conductor is zero. And that's the first important point regarding conductors in equilibrium. The second important point that's addressed in this chapter is that any excess charge on the conductor will be on the surface of the conductor. And an example is shown here with this illustration where we have an arbitrarily shaped copper conductor and we place excess charge on the conductor. So I've got a little animation to show the placement of that charge. So if we try to put a little charge in the middle of the conductor, it will disperse towards the outer surface, and a little more, it does the same, and a little more, it does the same. And what we find is that any excess charge placed on the conductor is going to move towards the surface of the conductor. And part of that can be understood intuitively in the sense that like charge wants to get away from other like charges. They're repulsed from each other, so they're going to move to the surface where they can spread out as far as possible. And to do a proof is outlined on the right-hand side of the slide. We can consider a Gaussian surface just inside the surface of the conductor as shown. So this little black line represents a Gaussian surface just inside of the conductor. And since we know that the electric field inside the conductor has to be zero when it's in equilibrium, that means that E is equal to zero at every point along this Gaussian surface. And since E is equal to zero, then the flux through that Gaussian surface is going to work out to be zero. And therefore, by Gauss's law, we can say that the charge inside is equal to zero. So this is the standard Gauss's law proof to show that the excess charge inside the conductor is going to be equal to zero. Okay, so these two properties are summarized here. The first is the electric field inside a conductor in static equilibrium is zero. And the second is any excess charge will be on the surface of the conductor. And these two properties are something that we can put to use when we're solving problems that involve conductors in static equilibrium. Okay, so we'll work one example now making use of these two properties together with Gauss's law. And this is problem 35 from chapter 24, and it describes a neutral conductor. And it says the conductor contains a hollow cavity in which there is a 100 nanocoulomb point charge. So I'm going to sketch the conductor with a hollow cavity. And we have placed a point charge in the center of the hollow cavity, which has a positive charge, and I'll write that as plus Q, or actually maybe I'll write that as Q1, because there'll be two different charges here, and Q1 is equal to 100 nanocoulombs. And then we're told that a charged rod then transfers negative 50 nanocoulombs to the conductor. So on the conductor, there is a negative charge, which is Q2, and Q2 is equal to negative 50 nanocoulombs. And writing those values out in SI units is 100 times 10 to the minus 9 coulombs, and then negative 50 times 10 to the minus 9 coulombs. And the question is, after we do this charge transfer, what is the charge A on the inner wall of the cavity wall? And so we're looking for the charge on this inside surface of the cavity. And that I'll call Q interior. And then on the second part of the problem, we're looking for the charge on the exterior surface of the conductor. And so that's going to be the charge on the outside surface of the conductor. And that'll be the charge out here. And that I'll call Q exterior. And those are our two target values. So we're looking for Q interior for part A and Q exterior for part B. And this surface here is meant to be the conductor. I've drawn it as a spherical shell. And then it has a hole cut out of it in the center, and that's where the charge plus Q1 resides as a positive charge. Okay, so that's our setup. We've got a positive charge in the hollow of the conducting spherical shell, and we've got negative charge, Q2, applied to the conducting shell, and we're interested in determining how much of that excess charge, Q2, is lining the interior surface of the conductor and how much is left over on the exterior surface. What we know is that all of the excess charge will be on the surface of the conductor, so none of it will reside inside the conducting shell. So to answer this problem, there's a couple principles that we can bring out. One is charge conservation. So if the charge on the conducting shell is split between the interior and the exterior surface, then we know that the sum of those two charges must equal the total excess charge on the conducting sphere. So this will be equation 1, and it will allow us to solve for the charge on the exterior of the conducting shell if we can figure out the charge on the interior surface. We can rearrange it to solve for Q exterior, and this I'll call equation 1. So we next turn our attention then to trying to find Q interior. And to figure that out, I am going to use a trick that's used to solve such problems. And the strategy is that I choose a Gaussian surface which is inside of the conductor. So my Gaussian surface is a Gaussian spherical surface inside the conductor. And the reason I place it inside the conductor is because I know that the electric field is everywhere zero inside. So that if I try to apply a Gauss's law analysis to this Gaussian spherical surface, I would find that the flux through the surface, since E is zero everywhere along the surface, the flux is going to be equal to zero. And if the electric flux is equal to zero, then by Gauss's law, that's equal to the charge inside the Gaussian surface divided by epsilon naught. And so this implies that the charge inside my chosen Gaussian surface is equal to zero. I next look to see how much charge is inside my Gaussian spherical surface. And what I note is that the charge inside the Gaussian surface consists of the charge on the interior surface of the shell plus the charge at the center of the hollow. And so Q in is equal to Q interior plus Q1. And that implies, since Q in is equal to zero, that Q interior must equal the negative of the charge on the inside of the hollow, which is Q1. So Q interior then is equal to negative 100 nanocoulombs. Plugging in the value of Q1 that we have. So that means that I have a positive charge at the center, which is equal to plus 100 nanocoulombs. What we have just reasoned out is that the charge on the inside surface of the conductor must be equal and opposite to the charge at the center. So in other words, by placing the positive charge in the center of the hollow, we polarized the charge on the conducting shell to draw enough negative charge inwards to just cancel the charge in the center of the hollow. So Q interior is equal to a negative charge of negative 100 nanocoulombs. Then to find Q exterior, I go back to equation 1, and I see that Q exterior is going to be equal to negative 50 nanocoulombs, because that's Q2 minus negative 100 nanocoulombs, which will leave 50 nanocoulombs for the exterior surface. And so on the exterior surface, we've got a positive charge. And the net of this charge on the inside surface of the conductor plus the charge on the outside surface of the conductor has to equal the excess charge that was applied to the conductor. So we've got negative 100 nanocoulombs on the interior surface plus 50 nanocoulombs on the outside surface. And if we add those two together, we get back our original Q2 value. So effectively, by placing the positive charge Q1 in the center of the hollow, we polarize the charge on the conducting shell. And using Gauss's law, we're able to figure out exactly how much charge we're going to have on the interior and exterior surface. Okay, so I'm just going to flip back for a second. The main ideas that we're making use of here in our analysis is that the electric field inside the conductor in equilibrium, that is, once the charges have been given a chance to come to rest, is going to be equal to 0. And we've also used the fact that we know that any excess charge will reside on the surface or surfaces of the conductor. And then I'll give you a clicker question to think about these ideas and to apply them to a different case. And then we'll come back with the last part of the lecture, where we'll discuss more attributes of conductors in equilibrium.